This lesson will be about using Taylor and Maclaurin series to represent three functions in specific: e to the x, y equals sine of x, and y equals cosine of x. So just to recall, this is Taylor's theorem. I've made some notes in red. So we have f of x equals this expression. You can refer to a previous video if this isn't making sense. But just a note that this f with the superscripted parenthetical n, that means the nth derivative evaluated at a, because we're plugging in a. And then a little note for what a is: it's the center of the power series. We'll discuss why it's called a center later on in this lesson. For now though, if we let the center be 0, or if a equals 0, we get, instead of this thing, we get this. And this would be Maclaurin series. So I guess a Maclaurin is just a Taylor with center 0. So we're going to start, basically the thing that we really need to dig into, or the unique identifier for each function. Think of each function as having its own DNA. And in order to sequence that DNA, really what we need to know is that guy. And more specifically, if all of them have this n factorial in it, we really just need to figure out what's going on with the numerator of the coefficient. In other words, what is the nth derivative of the function evaluated at a given point? In this case, evaluated at 0. So we want to name some functions that we haven't already dealt with. For example, we dealt with a function like that one. We dealt with that using a geometric series. We were able to produce things like arctangent of x. All of these were developed using either a geometric series or a little tweak on the geometricity. So now we're worried about functions who don't seem to have any tie to a geometric series, like e to the x, sine of x, and cosine of x. They don't seem to have a direct tie to the geometric series. So we appeal to this thing, which is our means of figuring out the polynomial coefficients. So we are supposing this. We're supposing that e to the x equals some polynomial. And we don't know what the polynomial is, but what we need to be able to identify is, does it have an x to the first? Does it have an x to the second? Does it have an x to the third? If it does, how many of those does it have? That's the main question. Well, the way to figure that out, first of all, let's declare this to be f of x. I'm going to write that a little neater. We'll declare our function that we're examining to be e to the x. So we have to take a bunch of derivatives and figure out a pattern so that we can figure out what this numerator is. The denominator's got the same thing every time. It's always going to be however many derivatives you've taken, that number factorial. So we take f prime, or f single prime, of e to the x, and of course that's e to the x. And f double prime of e to the x is e to the x. And now you can see why we've chosen e to the x to be our first exploration into Taylor and Maclaurin series. In fact, any derivative, no matter how many we take, I've named it as the nth derivative, is going to be e to the x. And if that's the case, then all of these things, when we evaluate them at 0, e to the 0, in all cases here, is 1. Now what does that mean? Well, go back to the Maclaurin series. That means every single time, whatever power of x you're wondering about, you could put a 1 in the numerator for that particular power of x's coefficient. So for example, if I were to write this in more detail, we could say the 0th derivative evaluated at 0 is 1. The first derivative evaluated at 0 is 1. The second derivative evaluated at 0 is 1. So now we can generalize that e to the x, so f of x, which is e to the x, is equal to this infinite sum. But one thing that we know, that we've learned here, is that that is always 1 for the e function only. And e is the only function that has this property, and then we multiply by x to the n. So for example, well, I could write this a little bit more concisely. And if we wanted to write this out, rather than having a sigma representation, we could let n equal 0. That'll give you 1, and then over 0 factorial is 1. And then when we let n equal 1, we get x to the n over 1 factorial. And then, when we let n equal 1, it's x to the 1. Now n equal 2 will be x to the 2 over 2 factorial. And then you can keep this going, x to the 3 over 3 factorial. And this thing is the E series. And what that means is, if you want to uniquely identify the e to the x function, it's the function whose polynomial DNA can be written as 1 over whatever the power is factorial. So I'll talk more about what this center means in the context of a sine or cosine function. I think it's a bit more graphically interesting there. So for now, what you can take away is that the e to the x function is that. So I'm going to store that up here. E to the x is that infinite sum. Most importantly, it's 1 over n factorial for any power of x, for any n power of x. Okay, the next function we're going to look at is the sine function. So now we'll let f of x equal sine. First thing to note, we need to find a bunch of derivatives, but the derivatives can't possibly be simpler than e. E's derivative every single time is e to the x, or e to the x's derivative is e to the x, which means we can predict exactly what that numerator will be, and it'll be the same thing every time. So for sine, it's a little different, because f prime, maybe you want to hit pause and write a bunch of derivatives down for yourself. I'm going to go up to the 5th derivative. Okay, now I have 5 derivatives here, or 6 different terms. So each one of these things, when I plug 0 into them, is going to tell me the numerator of the coefficient. So f of 0 is sine of 0, which is 0. And in fact, you might see that that's got sine, sine, and sine. So f double prime of 0 has to be 0, and f fourth prime of 0 has to be 0. By the way, the notational convention here is you can write tick marks, but after 3 tick marks, it's a little bit laborious, so we put the number in parentheses. If you don't list a number in parentheses, it's not proper notation. Now, what you'll notice is these are important ones, because f prime of 0 is finally not 0. In fact, cosine of 0 is 1. And f triple prime of 0, that's negative cosine of 0, which is negative 1. And then we go to the 5th derivative, and it's back to positive 1. So one thing you'll notice about sine is it turns off all the even derivatives. By that I mean the 2nd derivative, the 4th derivative, the 6th derivative, or even the 0th derivative. And it turns on all the odds. When I say turns on, I mean it has some. So like x to the 5th, there are some x to the 5ths because it has a non-zero numerator. But for example, are there any x to the 4ths in the sine function? The answer is no, because x to the 4th has to have this as its numerator and its coefficient, and there's nothing there to be had. So if we're writing the sine function, remember we're going term by term here, and it might be useful for us to have I guess to write it out. So the first one would be f evaluated at 0 over 0 factorial times x to the 0. This is true for any function. That'll be its first term. Well, for us, and then we'll have the first derivative evaluated at 0 over 1 factorial x to the 1, etc. I'll write a bunch out. A lot of writing here. Hopefully I've made no mistake. So now what we're going to do is go in. I hope you can see all of those. Yeah, it looks like they just squeezed in. We're going to go in and we know that, for example, 0th, 2nd, and 4th are all gone. So these terms, that doesn't exist because f of 0 is 0. So that whole term zeroes out, that term zeroes out, and that term zeroes out. So what do we have left? Well, f of x is sine of x. F prime of 0, that's 1. X to the first. And then f triple prime of 0 is negative 1. So it's minus 1 over 3 factorial x cubed. And then we have an x to the 5th that's going to be positive 1 over 5 factorial x to the 5th. And then I'm sure you can predict the next one, but it's going to be negative 1 over 7 factorial x to the 7th. So the sine function notably zeroed out all the evens. Now think back to what you know about the sine function from your pre-calculus knowledge, from trigonometry and from the graphs. Sine is an odd function, right? If we graph sine, we get a graph that happens to be symmetric about the origin. So something like this. And that symmetric about the origin means an odd function, but what we can conclude from Taylor and Maclaurin's insights is that it's odd because the DNA that it's built on is odd, right? If all the odd powers are turned on, there are odd powers here, but there's not a single even power. So that's an insight into the nature of the sine function that we wouldn't have had otherwise. Now, I want to talk a little bit about what this center means. And we could keep this going, right? And you could even generalize it for in a sigma notation. I'm not going to bother with that right now, though. What I want to do is look at the graph. If we were to graph each of these in pieces, so if we were to graph, for example, I'm going to write it in green here. If we were to graph y equals x, I'll put it next to my graph here. We're going to graph y equals x, which is what that is. So if I graph y equals x, it looks like this. Looks something like that. Now, in black, I'm going to graph y equals x minus x cubed over 3 factorial. I have it on my calculator here. Okay, so that's just the first two terms. So y equals x represents just this term, and then y equals x minus x cubed over 3 factorial represents this one. So you can imagine we're trying to get to this blue sine wave that's here, and a line is a pretty crude approximation. It's actually a really good approximation. If you're looking just in a very small window, you can't really tell the difference between the linear function y equals x and sine of x. That's why we call A the center, because at values near A, or near the center of 0, this thing is really good at approximating sine. So if you plugged in 0 or 0.01 to this polynomial, or if you plugged it into the actual sine function, you're going to get very close approximations. The further out you go from 0, so if you plug 10 in, this y equals x is going to give you 10 as the output, whereas the sinusoidal function is going to give a wildly different response. Now, what this black curve here is doing, this is y equals x minus x cubed over 3. It's actually taking a linear function and bending it down on the right side and bending it up on the left. So it's actually adding a little bit of accuracy. So it gets closer to this relative max and this relative max. My picture's not perfect, but it's okay. And then in red, I'll do the next one, which is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. So now that's using all three of these terms. I'm going to use my calculator again here. And again, it's not perfect. You can make a picture in your own calculator. So that's the graph of this red function. And what that's doing, again, it's adding another bit of, and as opposed to the black function, which dives down here, it's trying to correct this black curve a little bit by bending it up. And if we repeatedly bend up and down, you can imagine taking just a line or like a piece of metal, like a wire. You bend it down at this first hill, you bend it up at the next, and then you keep doing that. And what all these odd powers are doing is it's adjusting both sides so that it fits the sine. And the center is really important because at the center, they exactly agree, regardless of what your approximation is. And to numerically conceive of this, think about sine of 0. And sine of 0 is, of course, 0. If you plug 0 in any number of terms here, you get exactly 0. That's what makes the center the center. So if we wanted to use pi as the center, so everywhere in here, we'd have x minus pi in for x here. What that does, it takes the whole function and just shifts it to the right. And what that does is means if you plug in numbers really close to pi, you're going to get a very close approximation to the sine function. Just like here, if we plug in numbers close to 0, we're doing really good. We're getting close to the actual value. So if you want to move the center, it's really arbitrary. Maclaurin series, by convention, is with a center of 0. Now, if we do the same exact process that we've gone through here for cosine, so if we use f of x as cos, you'll find that the first derivative is negative sine. That thing is going to have first derivative value of 0, which means it's going to turn off the odds, but the evens will be switched back on. In other words, they won't be 0 anymore. So every odd number, and now think about what that means for cosine. Cosine will have, it'll start with one single 1, or 1x to the 0, and then it's going to subtract out x to the 2 over 2 factorial, add in x to the 4th over 4 factorial, etc. Because cosine's an even function. An even function, by its nature, is going to have only even-powered terms. It's not going to be the sum of evens and odds. The mystery that I'll leave to you here, maybe for another video, is the fact that the e function takes on all powers, right? Even and odd powers. It has them represented. The sine function goes every other, but it only uses odds, and it switches its sign from positive to negative. Cosine does that same game with even powers. So the question is, how does e relate back to sine and cosine? We'll answer that another day.